everybody, so this is going to be the lecture video for section 5.4, the fundamental theorem of calculus. And so kind of just by its title, you can probably guess that this is a really important theorem. And it's going to basically connect the two big ideas that we've seen in this calculus course. And so those two ideas are going to be the derivative and then our integral, so derivatives and antiderivatives. So if you remember in the last section, in section 5.3, we learned about the definite integral. So we saw that when we have the integral notation with bounds a to b on the integral, this represents the signed area under the curve f of x on the interval a to b. And so we say signed area because if the function f is above the x-axis, our area is going to be positive. But when our function is below the x-axis, the area is negative. So sometimes you're going to have all negative area, sometimes you would have all positive area, and sometimes there's a combination of the two, and so, some of the negative area cancels out some of the positive area. And so we refer to this as signed area because of its potential to be negative. So we also learned about some properties of the definite integral. So certain things that we saw were that if you switch the order of the bounds, it changes the sign of the area. So if it was negative before, it would become positive, and if it's positive, it becomes negative. So that's what happens when you switch the bounds. We also saw that the integral from a number to itself, so from 3 to 3 or 4 to 4, we saw that that area is always 0 because we're talking about the area under a single point, which is 0. And then another property that we saw that is really useful is that we can split up the integral. And we can do this in a couple of ways. If we have two functions being added, then we can break it up into the integral of each function individually and then add them. Same with subtraction. And we saw that if we wanted to split the bounds, so let's say our bounds were originally 0 to 5, we could split it up as 0 to 2 and then 2 to 5 as an example, or we could do something like 0 to 1, 1 to 3, and 3 to 5. So you could split it up as 2 or 3 or more integrals along that same interval a to b. So we saw that as well. And so what I want you to sort of think of here is, and this more alludes to section 5.5, but our integral behaves very similar to our derivative. We were allowed to break up our derivatives if functions were being added or subtracted, and we could just take the derivative separately and then add them or subtract them. And these were things that we could do. We could multiply them by a constant. That's something that we can do with the integral as well. And you can imagine that just like with derivatives, how multiplication and division made it more complicated and we had to learn these different rules like the product and quotient rule, that is also going to happen with the integral. But we'll see that in section 5.5. Okay, so let's just give ourselves a reminder here. So our relationship between the antiderivative and the derivative is as follows. So if oops, I'm still writing in blue. Oh, well, that's fine. So if capital F of x is our antiderivative of little f of x, and so remember the notation that we use for this is also an integral notation, but it's an integral without bounds, so we call this the indefinite integral. So if capital F of x is equal to the antiderivative of little f of x, then what that means is that the derivative big F prime is equal to our original function, little f. And we call big F of x our antiderivative. The antiderivative of little f of x. Okay, so again, this concept of an antiderivative, the concept is we are going backwards. So we have the derivative of a function and we're going back to the original function. You can think of it that way. So we're finding a function whose derivative is the one that we're looking at. So this leads to the following theorem. So the fundamental theorem of calculus is actually split up into two parts. Most people find part one to be the most challenging and unintuitive, and my claim is actually once you learn part two, part one seems a bit more clear. But part one is saying this. So the fundamental theorem of calculus part one says, okay, if we have a continuous function f on an interval a to b, then big F of x, if we set big F of x equal to the integral from some number a to x of little f of t dt, we'll talk about this in a moment. So if big F of x equals this, if this is continuous, on a to b, and differentiable on the open interval, so and differentiable on the open interval a to b, so round brackets, and then its derivative is okay, so it's going to be the derivative of big F prime of x. Let's think about this for a second. So it might look at first glance like, okay, big F of x is going to be some sort of area because it's the definite integral of something, right? So it would be the area under the function little f of x between a and x. And so that's true, but because x is a variable, it's going to actually be like an arbitrary area function. It's what the area would equal for different values of x. And so we'd have some sort of function of x here, and when we take its derivative, so f prime, we're doing d by dx of our integral from a to x of f of t dt. And this theorem is telling us that this derivative is actually the original function evaluated at x, so little f of x. And so what this is showing us is that there is a very strong relationship between the antiderivative and the area, so the definite integral, right? So, so that's what this relationship is here. So the derivative of the antiderivative is the function in the integrand. And so what it may look like to you is that we just did nothing, right? We took the derivative of an antiderivative and we got back the original function that was there. And so it's this inverse relationship that's making this happen. Just like when we took sine of sine inverse of x, we just got x. It's the same sort of idea here. We're taking the derivative of the antiderivative of this f of x function and we're just getting back f of x. So that's sort of maybe a trick on how you can think about it. So let's look at some examples using this theorem. Okay, and so this theorem is very specific. Our integral has a constant in the bottom bound and a variable x in the top bound. So in our first example, we have big F of x is equal to the integral from 3 to x, so it's taking that same form. It's got a constant on the bottom bound and an x on the top bound. And then we've got this function little f of t here. So this guy here is little f of t. Okay, that's little f of t. That f doesn't look very good. Okay, and so we want to find big F prime of x. And so our fundamental theorem of calculus part 1 says that it's going to be this little f function evaluated at x. So instead of t cubed, it's going to be x cubed. And instead of the square root of t plus 2t to the 4 plus 1, it's going to be x plus 2x to the 4 to to the 4 plus 1. Okay. So then in our second example, there's a bit of an issue. So we are given the integral from x to 4 of e to the t cubed minus 9 over t squared plus 1. So again, this, this function here of t is just little f of t. But our bounds here, notice we don't have a constant on the bottom, we have a constant on the top. And in the fundamental theorem of calculus part 1, the way that it's stated is that the constant needs to be on the bottom. So we actually need to rewrite this with 4 on the bottom and x on the top. So we want to switch the bounds. But remember, if we switch the bounds, we need to change the sign. So it's going to be negative the integral from 4 to x. So this comes from our properties of the integral. And then again, our f of t function doesn't change. So it's still e to the t cubed minus 9 over t squared plus 1. Oops, t squared plus 1 dt. So if I want to find the derivative, our ultimate goal is to find g prime of 1, but I want to start off by finding big G prime of x. And so we are just going to have negative little f of x. So we take our f of t function, we plug in x for wherever we see a t, and we know that the sign on everything is going to be switched because we've changed the order of the bounds of the integral. So that changes the sign of our answer. So we're going to have minus e to the x cubed minus, plus, because we changed the sign, plus 9 over x squared plus 1. So then last but not least, if we want big G prime of 1, we're just taking x equals 1 and plugging that in. So we end up with negative e to the power of 1 plus 9 over 1 squared plus 1, which is 9 over 2. And that would be our answer. Okay, the next one is a little bit trickier. So if we look at our bounds, we have the integral from 1 to x squared. So again, this cube root function here, this is just our little f of t. So, that part's not too exciting. But our bounds, they kind of are good, but they're also different. So we do have a constant as our lower bound, which is what the fundamental theorem of calculus part 1 has. But our top bound is no longer just an x, it's an x squared. And so you might think, well, no problem. We'll just plug that x squared in for our t, just like we plugged the x in for our t. And you would be half correct there. That is something that we are going to do. But remember, we are taking a derivative here. So we need to also account for the chain rule. The fact that it's more than just x up there means we need to apply the chain rule to it. So we would need to multiply this by the derivative of our x squared after the fact. So let's write this down. So I'm going to say since the upper bound is an x squared, and not x, we need to apply the chain rule. And we need to do this because we are taking the derivative. So we need to apply the chain rule when taking the derivative. And again, all of this is going to make a lot more sense once we see the fundamental theorem of calculus part 2. So we will kind of come back and revisit these ideas. But okay, so what we would have then is we would have capital F prime of x. So it is still going to equal the little f function evaluated at x squared, but then it's going to be multiplied by the derivative of x squared, which is 2x. So that's going to be the cube root cube root of x squared squared, so that's going to be x to the power of 4, okay, plus 4, and then times 2x. So then, if we then want to find big F prime of -1, which is what the question is asking for, we're just going to evaluate this at x equals -1. So we're going to have the cube root of -1 to the power of 4, which is 1. So 1 plus 4, which is 5. And then it's going to be multiplied by -2. And so we end up with -2 times the cube root of 5 as our final answer. Okay. So one final example for the fundamental theorem of calculus part 1. And it's sort of combining these ideas that we just saw. So if we look at our function, we've got big F of x is equal to the integral from e to the x to 3x of our little f of t function. So this again is my little f of t. Okay, well, we probably feel like maybe we're in trouble here because both bounds are functions of x and neither of them are constants. And in the fundamental theorem of calculus part 1, we need to have a constant at the bottom. And so what we can think of is we can think of rewriting this. So remember that we're allowed to break up an antiderivative with numbers in between the two bounds. So with some value, some constant value that falls in between e to the x and 3x, we can break this up. So we can rewrite this as, so we want to introduce sort of a constant into this function. So we have f of x into this integral, I should say. Oops. So we have big F of x equals, and so I'm going to say that it's equal to the integral from e to the x to some constant c of our function, so ln of root t plus 5t cubed dt plus, and now I'm splitting it up again, this is going to be c to 3x of ln of root t plus 5t cubed dt. So let's just make this a little bit clearer to read. Okay, so this is kind of like what I was talking about when we were reviewing the first page. You can break up an integral going from, let's say, 0 to 5 as like 0 to 3 and 3 to 5. And so we're doing the same thing. We're going from e to the x to some constant c, and then from that same constant c to 3x. So we've broken up the integral, but now c is a constant value, which we need. Now, in the second integral that we have here, it's the integral from c to 3x. That we can directly apply the fundamental theorem of calculus part 1 to, because we've got the constant on the bottom. For our first integral, the constant is on the top, so we actually first need to switch the order of the bounds so that the constant falls on the bottom. But when we do that, that changes the sign of the integral. So it's now negative the integral from c to e to the x of this function ln of root t plus 5t cubed. That's a cubed dt. And like I said, we can leave our second one the same because it's already written in the correct order. Okay, so then if I want to take its derivative, big F prime of x, I'm going to have to use the fundamental theorem of calculus part 1 2 times. And in both cases, I'm going to need to use the chain rule because I have more than just x on my bound. I have functions of x. So in the first case, I have e to the x, and in the second case, I have 3x. So for the first integral, my derivative is going to be minus ln, so I'm plugging in e to the x wherever I see t, so I have root e to the x plus 5 e to the 3x, because that's what happens to e to the x when you cube it, so it's e to the 3x. And then I need to multiply this by the derivative of e to the x, which is just e to the x. So that second part's the chain rule. Plus, now for the second half of my derivative, I'm going to have ln, and everywhere I see a t, I'm going to plug in 3x. Okay, so I have root 3x plus 5 times 3x cubed. And then multiplied by 3, which is my derivative of 3x. So if I want to find big F prime of 1, like the question is asking, I just need to plug in x equals 1 now. So I'm going to have negative ln root e plus 5e cubed times e plus 3 times ln of root 3 plus 5 times 27. And whatever that equals as a number, that would be my answer. Okay, so that's the fundamental theorem of calculus part 1, but the more commonly used part of the fundamental theorem of calculus, so the second part you're going to use constantly. So this one is going to allow us to compute the area under the curve in a much quicker way than taking the limit of the Riemann sums. So remember, we talked about if we were able to take the limit as the number of rectangles goes to infinity, we would find the exact area under the curve. But that's a difficult limit to take, and so we've got this quick rule, which comes from the fundamental theorem of calculus part 2, and it's going to give us a fast way to find the area under a function on an interval. So the second part of the fundamental theorem of calculus states if we have a continuous function little f on a to b, and big F is any antiderivative of little f on that same interval. So when I'm saying any antiderivative, I'm saying it doesn't matter what the constant value is, right? So big F is an antiderivative of f on that interval. Then the area, so the integral from a to b is the area. So the area under my function little f of x dx is actually equal to our antiderivative evaluated at b minus our antiderivative evaluated at a. So this is actually something we've done before, and it's the one example that I keep referencing where we were talking about the velocity function and its relationship to the original position function. And when we had the graph of velocity and we wanted to find when we found the area underneath the velocity function on an interval a to b, we found that what that was giving us was the distance traveled, right? It gave us the position function at the far point, so let's call that b, minus the position function at the biggest point, so that would be s of a. So we saw that our integral of velocity is equal to equals to our position function evaluated at b minus our position function evaluated at a. And so that was actually just one example of the fundamental theorem of calculus part 2. So this is it in more general form. So what it's saying is to find the area, I just need to find the antiderivative and then evaluate it at the two endpoints. So let's work through an example. So we want to find the area under this curve, 5x squared plus 2, on the interval -1 to 3. So I'm looking to find, so my area I know is equal to the integral from -1 to 3 of 5x squared plus 2 dx. So that just means the area under this function between -1 and 3. So from the fundamental theorem of calculus part 2, we know that we need our antiderivative. So we need to find big F of x for our function. Well, big F of x, what does it equal? Let's find our antiderivative. So for 5x squared, what function is going to have derivative 5x squared? Well, we use the power rule. So it's going to be 5x to the power of 3. So we increase the exponent by 1, divided by 3. And then for the 2, what has derivative 2? 2x does. Oops. So 2x is going to be the next part of our antiderivative. Finally, what we always seem to put on our antiderivatives, because we know that when we take the derivative of a constant, it goes to 0, is we put this plus c there. So the fundamental theorem of calculus part 1 tells us that this area is actually equal to our antiderivative evaluated at the top bound, so at 3, minus the antiderivative evaluated at the lower bound, which is -1. So we need to take our capital F function and evaluate it at 3, and then evaluate it at -1 and take the difference of those two things. So that means we would have 5/3 evaluated at 3 cubed plus 2 times 3 plus some constant c minus, and now we're going to evaluate it at -1. So we're going to have 5/3 times -1 cubed plus 2 times -1 plus c. So the first thing that I want you to notice is that these plus c's cancel. Right? You have a plus c in the first part minus another plus c. And that's actually always going to happen when you have a definite integral. So when we have an integral with these numbers on the bounds, that means the plus c is always going to cancel. So in fact, we actually normally never put it there for a definite integral because it always cancels. The time that you want to have the plus c there is when there are no bounds on the integral. So if it was just the integral of 5x squared plus 2 and not the integral from -1 to 3 of 5x plus x squared plus 2, when it's just the indefinite integral, that's when we want to have the plus c there, when your final answer is the antiderivative. But when your final answer is an area, you don't need to have the plus c there because it's always going to cancel. So if we work this out, assuming I didn't make a mistake, I have 51 minus -11/3. And so I end up with 164/3. Oops. Okay, so I guess the little note that I made here is just that the plus c's are always going to cancel. So note plus c will always cancel. For a definite integral. So we don't bother putting it when we're talking about finding the signed area. The plus c doesn't need to be there. So let's work through another example. So we want to determine the integral from 0 to 1 of sine of 2x plus e to the 7x. And okay, so what we need to find is our antiderivative. So we're going to use some new notation. So I'm just going to make a note of that. So we will use new notation. So rather than writing, rather than trying to write, big f of x off to the side and figuring out the antiderivative sort of separately as side work, we're going to use some different notation here that's all sort of condensed in the same spot. So we're going to use some new notation. Okay, and so what we usually do when we're trying to evaluate this area is we start off by finding the antiderivative, just like we did in the last time, but you write it inside some brackets. So we're going to put our antiderivative in this box here. So this is where my big f of x is going to be put. Okay, so let's start by thinking of what our antiderivative would be. So starting with sine of 2x, well, what function is going to have derivative sine of 2x? You might think cosine of 2x, and you'd be close. So we can put cosine of 2x here. Okay, well, let's think about that. Is that right? What's the derivative of cosine of 2x? Well, the derivative of cosine is negative sine. So already I have a problem because this is a positive sine 2x. So I need to have a negative sign multiplied in front of this cosine so that when I take its derivative, it's going to be minus sine of x. So that would become a positive sine function. So the derivative of this negative cosine of 2x is going to be positive sine of 2x times 2, because there's a chain rule involved here, right? If because we have more than just x inside the angle brackets, we have a 2x. When we take its derivative, we need to multiply by that 2. But we can see in our function, we just want sine of 2x. We don't want it to be multiplied by 2. So in our antiderivative, we need to divide by that 2 so that when we take its derivative and multiply by 2, those 2's are going to cancel. Okay, so that's our antiderivative of the sine of 2x. For e to the 7x, well, what has derivative e to the 7x? You might say e to the 7x does, and you'd be close. So again, let's think about this guy's derivative. Because of the 7x in the exponent, we need to use the chain rule. So our derivative would be e to the 7x, so we keep that exponential function the same, but then we multiply it by the derivative of the exponent. So we would multiply it by 7. So in our antiderivative, we need to do the opposite. We need to divide by that 7 so that it cancels when we take its derivative. Now notice I didn't put a plus c here because we are solving an area. We're solving a definite integral, so we don't need the plus c. Okay? So with this new notation, we want to have our antiderivative written inside some big brackets, and then what we put next to it to indicate that we still need to evaluate it between the bounds 0 and 1 is we use this line, which we've used before with the d by dx notation. So we use this line and we put the bottom bound on the bottom and the top bound on the top. So this line here, this line with a 0 and 1 on it, this means evaluated. This is indicating that we still need to evaluate. So it means evaluated at x equals 0 and x equals 1. And it's specifically telling us that we need to do it in the order of the fundamental theorem of calculus, which says we take big F of our top bound minus big F of the bottom bound. So it's always the top one evaluated minus the bottom one evaluated. So that's the notation that we're going to use. Okay, it's a lot more condensed. So now let's actually do the evaluation. So we start off by evaluating with the top bound with 1. So we have minus cosine of 2 over 2 plus e to the 7 over 7 minus, now we want to evaluate at x equals 0, so we have minus cosine of 0 over 2 plus e to the 0 over 7. So simplifying this, or you can plug it into your calculator if you want to get a decimal answer. So that would be 171,799.47 roughly. This is a huge area under this function. Okay, let's do another example. So we want to determine the area under the function x cubed minus 1 over x plus root x, and between the bounds -1 and 2. Oh, actually, sorry, there was an error on this. We actually want it to be between +1 and 2. So between, actually, I might actually just be able to erase the sign. Yeah, so we want the integral to be going between 1 and 2. And so we want to start off by finding the antiderivative for this function. But if I look at this function, notice the square root there. If we want to take its antiderivative, just like when we were taking derivatives, it's not a bad idea to first rewrite this in terms of powers of x. So I would rewrite this definite integral as the integral from 1 to 2. And so I'm going to keep x cubed the way it is. 1 over x I'm not going to rewrite as x to the -1. If you remember in section 4.8, this is the 1 power of x that we want to keep in the denominator because its antiderivative is a ln function. But that square root of x I want to rewrite as x to the power of 1/2 dx. Okay, so we've rewritten this. Now our first step is to find our antiderivative, and we want to put it into a nice square box. So for x cubed, our antiderivative, we increase the power by 1, so it's x to the power 4, and then we divide by that same power, so divided by 4. For the minus 1 over x, we know that ln of x is going to have that derivative of 1 over x. We can put the absolute value of x, but notice we don't actually need the absolute value here because our bounds are going between 1 and 2. So you don't have to have the absolute value there. And for x to the 1/2, we use the power rule again, which tells us to increase the power by 1. So it's now going to be to the 3/2. And then we want to divide by 3/2, which is the same thing as multiplying by 2/3. Okay, and so that's our antiderivative. We still need to evaluate it between 1 and 2, so we put the line there to acknowledge that. So now evaluating it, we start by plugging in the top bound first. So we're going to have 2 to the 4 over 4 minus ln 2 plus 2/3 times 2 to the 3/2. Okay, minus evaluating at our bottom bound. So that was going to be a 1 over 4 minus ln 1. We know that ln of 1 is 0 plus 2/3 times 1 to the power of 3 over 2. Well, 1 to the power of 3 over 2 is just 1, so that's pretty easy to do a lot of this one in our head. So we end up with 4 minus ln 2 plus 2 to the power of 5 over 2, so I just combine my exponents there. So my 2 is to the power of 1, and then it's multiplied by a 2 to the power of 3 over 2. So I add 1 plus 3 over 2 to get the 5 over 2. That's still divided by 3, minus 1/4 minus 2/3. So if I wanted to have an exact answer for my math lab, I could combine my 4, my 1 over 4, and my negative 2/3 into a number, but the other two parts would have to stay as they are because they would just have decimal answers. But if I want to find it as a decimal, let's say to the nearest hundredth, it would be 4.28. Okay, so depending on how MyMathLab wants your answer, you may need to be able to do some simplification, or you may need to be able to plug it into your calculator and round. It just depends on how they ask for the answer. Okay, so one thing that we've talked about is that our integral represents the signed area. So since the definite integral represents the signed area, or we could think of this as the net area, so the negative area cancels out with the positive area, how could we find the total area under F? So when I'm talking about the word total area, what that means is that we count the negative area as a positive area. So anything that appears underneath the x-axis, we would actually want to count that as a positive area. So our answer is that we would need to know where the curve is under the x-axis so that we could take the absolute value of that area. Because we know when we use this technique of the indefinite integral by using antiderivatives and the fundamental theorem of calculus, when we use that method, what we're getting is the signed area. So if I don't want the signed area, I need to actually know where that area was originally negative so that I can take its absolute value to make it positive. So let's look at an example here, a drawing of what we're saying. So let's consider the graph of f of x that's given below. And the question here is saying set up the definite integrals which determine the signed area under the function between -6 to 6. So let's start off by shading in that area. So maybe I'll use just a different colored pen. So I want the area between -6 and +6. So this area here, and here, and here. So this is the area that I want. And the first question is saying, well, what's the definite integral which represents the signed area? Well, the signed area is just the definite integral. The definite integral gives us signed area. So that's just going to be the integral going from -6 to 6 of little f of x dx. That integral is going to count the area that falls below the x-axis as negative area and the area that falls above the x-axis as positive area. So maybe let's sort of indicate this. So this area here is negative. This area here is positive, and then this area in the final piece here is negative again because it's below the x-axis. And so your definite integral is going to count, from minus 6 to 6, we'll count this as negative, positive, negative, and it'll just take the difference between all of those values. So probably your final answer would be a negative number because there's more negative area than there is positive area. But the next question is asking us to set up the definite integrals which determine the total area under f on the interval negative 6 to 6. And so we want to find the area, but we'd like to count these two end pieces that are underneath the x-axis as positive area. And so if I take the integral going from negative 6 to 6, it's going to count those two end pieces as negative. And so you might think, well, okay, just take the absolute value of whatever I wrote down for the signed area. Just take the absolute value of your final answer and it will be positive. That's true, but I've already taken the difference between them. So what I mean by that, and I'll write it off to the side here, is, for example, if I want to take the absolute value of negative 3 plus 1 versus the absolute value of negative 3 plus the absolute value of 1, we're not going to get the same answer here. So let's think about this. The absolute value of negative 3 plus 1 is equal to the absolute value of negative 2, which is just going to equal 2. Versus if I take the absolute value of negative 3 first, separately I get 3 plus 1, and so that absolute value is 4. And so you'll notice when I take the absolute value of the negative number separately, I get a much bigger answer at the end because I haven't taken that net difference at first. And so it's the same sort of idea with the area. I don't want to take the absolute value of the difference between the areas. I want to take the absolute value of each piece individually. So I need to actually break up my integral into the parts where it's positive and the parts where it's negative. So we can see between negative 6 and negative 4, not perfectly, but pretend like that's going perfectly through negative 4. Between negative 6 and negative 4, my area is going to be negative. Between negative 4 and 2, my area is positive. Between 2 and 6, my area is negative. And so I want to break up my integral that way. So I'm going to say that my total area is equal to, so I'm going to have the integral from negative 6 to negative 4 of my function. And so that is negative area. I know that this is negative area. So this is negative area because that's where my function is below the x-axis. So if I put a negative 1 multiplied out in front of my integral, it's going to turn it into a positive area. So this will turn it, this will make it positive. Positive. Okay. Then the next piece between negative 4 and 2 is actually already positive. So I don't need to do anything to my definite integral. It's already giving me the positive area because that function there lies above the x-axis. But then the final piece from 2 to 6, that again is below the x-axis, so it's negative area. So instead of adding it, I actually want to subtract it to make it positive again. So this is how you can do it. Another way to write this would be to write this as the absolute value of the area between negative 6 and 4. Right? That's the same as multiplying it by negative 1 because it's negative there. Plus the integral from negative 4 to 2 of f of x dx plus the absolute value. So instead of subtracting this last integral to make it positive, I can just add the absolute value of this area, and that does the same thing. So both of these methods will work, and I didn't need an absolute value on the middle guy, the middle integral, because it's already positive there. So let's work through an example. So we want to determine the total area under this curve on the interval 0 to 4. So keep in mind, because it's the total area, we want all of our area to be counted as positive. We never want it to be negative if it's below the x-axis. So the first thing we need to determine is where does our function cross the x-axis on that interval? Because if it's crossing the x-axis, that means that we're going to have some positive area and some negative area. So when we're asking about finding where something crosses the x-axis, we're asking for the x-intercepts. So we set our function equal to 0, and we factor it. Oops. So x cubed minus 4x is set equal to 0. We can factor out an x, and we're left with x squared minus 4. And so that tells us that our x-intercepts on the entire domain are x equals 0 and then plus or minus 2. So if we're talking about on the interval 0 to 4, it's only going to cross the x-axis on that interval at 2. At 0 it also crosses, but that's an endpoint, so it doesn't matter. So we're looking for values in between 0 and 4 where it crosses. So we can say, so it crosses the x-axis at x equals 2 between 0 and 4. Okay, so now if we want to find the total area, we can take the absolute values of the parts of the function that are negative. Now, here's a note. We could first determine which part of the function lies under the x-axis and then only take the absolute value of the part that we know is negative. Or, if we want to be a little bit lazy, we could simply just take the absolute value of each part of the integral, breaking it up based on the x-intercepts. So we don't actually need to know where it's negative and where it's positive, because taking the absolute value of a positive number doesn't change it at all. So if I scroll back up here for a minute, in this final line here where I took the absolute value of the two negative parts, if I had taken the absolute value of that third part in the middle, the integral from negative 4 to 2, my answer still would have been the same thing, because that integral was already positive. That area was already positive there, so taking its absolute value doesn't hurt it. What is not the same thing, and that's what I wrote above here, what is not the same thing is taking the absolute value of the entire thing versus taking the absolute value separately. So you do need to take the absolute value, like you need to break it up into the parts where it's crossing the x-axis, the 3 parts in this example here. You can't just take the absolute value of the area that's written here, so from negative 6 to 6. You can't just take the absolute value of that. You do need to break it up, but you don't actually need to figure out where it's negative and where it's positive. You can just take the absolute value of each piece, and it won't change your answer. So what I mean by this, for this example, so we know on our integral from 0 to 4, we should be breaking it up at 2. So my total area is equal to, so we can think of this as it's the integral from 0 to 4, but we want the function to be positive the entire time. So x cubed minus 4x dx. Now you might be thinking, well, Brittany, you just said you can't put the absolute value on the entire integral. That is not what I did here. I did not put the absolute value. I'm going to erase this in a second. I didn't put it outside here. I put it on the function. Okay, so we don't want the absolute value on the outside there. By putting it on the function, I'm saying I want the integrals, though the area between 0 and 4, but I want my y values of my function to always be positive. So wherever they're negative, I want them to get flipped up and be made positive. But the way that we do this is by splitting up this integral. So we take the absolute value, so now I'm putting the absolute value on the outside of the integral from 0 to 2, so that's our x-intercept of this x cubed minus 4x dx. Plus, we take the absolute value going from 2 to 4 of the same function. So what happens is one of these areas is going to be positive and one of them is going to be negative, and we're taking the absolute value of both of them individually. So the positive one is just going to stay the same, but the negative one is going to be turned positive, which is what we want. So let's actually work this out. If I want to compute the area from 0 to 2 of this function, I start off by finding its antiderivative, so I'm going to put a square bracket there. So my antiderivative of x cubed is going to be x to the power 4 over 4 minus my antiderivative for 4x is going to be 4x squared divided by 2. So it's 2x squared once you simplify it. Okay, and if you want to double check that, imagine taking this derivative of 2x squared, you would get 4x, which is exactly what we want to get. Now I need to still indicate that we have to evaluate between the bounds 0 and 2, and we're taking the absolute value of that. Now for the second part, it's actually the exact same antiderivative, so we don't need to spend any more time thinking about the antiderivative. It's the exact same function. So the antiderivative is still x to the 4 over 4. Let me just write that a little bit nicer. So it's x to the 4 over 4 minus 4x, so minus 2x squared, that's the antiderivative of 4x. And now for this one, we want to evaluate between the bounds 2 and 4. Okay, so now let's evaluate. Plugging in x equals 2, we're going to have 16 over 4 minus 2 times 4. If I plug in 0, so I subtract my bottom bound, I actually just get 0. Plus, now plugging in my top bound, I'm going to have 4 to the power 4 divided by 4, minus 2 times 16, because that's 4 squared, minus my bottom bound being plugged in, which is going to be 16 over 4, minus 2 times 4. Okay, so I want to work this out now. Okay, the first one, I get the absolute value of -4 once I collect all, cancel all like terms, and plus the absolute value of 36. So we can actually tell our function was positive above the x-axis on the interval 2 to 4, and it was below the x-axis between 0 and 2, which is why we got a negative area between 0 and 2 and a positive area between 2 and 4. So now we just want to take the absolute value of that negative area, so it becomes 4 plus 36, and so we get a total area of 40. And so that's how you find the total area of a function. So it's always the same procedure. You need to find the x-intercepts, break up your integral by the x-intercepts, and then just take the absolute value of each piece individually. Some of those absolute values will be unnecessary, but they're not going to change your answer. Okay, so that is it for the fundamental theorem of calculus. In the final section for this course, section 5.5, we're going to be learning about how to take the antiderivative when the function has some multiplication or division in it. So when we can't just use this power rule here. All right, thanks so much for listening, and enjoy the rest of your day.